He graduated Seoul National University and Purdue University for his degrees. He has worked at Samsung and UT Austin as a postdoctor. He's been a professor at Posttech and moved to KAIST at 2019. Let me introduce you to our research areas. Our lab has various research topics very close to the state of art. Extending the scale of the system, investigating new spectrum bands, targeting the node moving at very high speed, and applying new methodologies are the solutions for the market needs. As you can see from the figure, real-time VR and AR online contents, vehicular communications for autonomous driving, cloud computing, edge computing, and factory automation are the upcoming applications with the potential that can totally change our daily life. Our research interests follow the technical requirements coming from these applications. First, I will explain some of the theoretical research areas. Massive MIMO communication systems are systems with an enormous number of antenna ports. MIMO stands for multiple input and multiple output, and a large number of antennas contributes to the channel Hardy effect, which results in a good channel condition. However, the pros and cons of the massive MIMO system is the power consumption. Under the power constraint, the low-bit analog to digital converter has been introduced to implement the large-scale array antenna systems. Even though the analog to digital converter degrades the signal quality, our research team developed a system that still works well with the low-bit ADC. Next is an intelligent reflecting surface, or also known as reconfigurable intelligent surface, which is literally the system with the reflecting surface. The reflecting surface is reconfigurable, and it relays the signal from the source to the sink. The reflecting surface consists of the passive elements that are only designed to shift the phase of signal, and the passive elements consume low power. Despite its simple functionality, experimental results that prove its necessity are widely reported. Our researchers are developing the cost-efficient techniques for the practical use of IRS, or also known as RIS. Another extension of wireless communications is the satellites. As widely known, the Starlink has launched thousands of satellites using the reusable rocket. The Starlink satellites nearly cover Earth, which has made it possible to support the network even under the destructive war. Geostationary orbit systems and low Earth orbit satellites are two types of satellites. To manipulate the satellite system, we're developing a simulator that models the movement of GEO and LEO satellites and will deal with the interference scenario where GEO and LEO satellites affect each other. Millimeter wave communication system is a system with a band of millimeter wave scale wavelength. The millimeter wave band is a higher than the conventional service band. Thus, the electromagnetic properties change. The channel sparsity is one of the main properties of the millimeter wave band. We have developed various communication techniques to exploit the properties of high-frequency channels. Furthermore, recent efforts are being made to extend the frequency band to terahertz range. This extension will allow us for the installation of more antennas, enabling the use of extremely large MIMO systems which surpass the capabilities of massive MIMO. However, as the traditional far field assumption becomes invalid in these scenarios, there is a need for research into the near field communications. Our lab is also working on this area of research. Next, wireless communication system and radar system both use the electromagnetic wave, which means that the wireless communication signal can detect the object and the radar signal can convey the data at the same time. Our previous work has proved that the signal of wireless LAN standard can take the radar image. Our research team has our own ray tracing simulator, very versatile to evaluate the performance of schemes. It's easy to show the coverage and service quality in the visible way. As the current communication techniques have largely been depending on the geometrical characteristics of wireless communication channels, the importance of this kind of simulator increases. Next is a machine learning, especially deep learning, has provided the solutions for huge engineering areas. One of our works related to deep learning was to extrapolate the downlink channel from the uplink channel. The uplink channel and downlink channels are different, and it is very difficult to infer the uplink channel from the downlink and vice versa. When using the deep neural network combining the fully connected layer and convolutional layer, our work has proved that the channel extrapolation is possible. We're also conducting research on applied deep learning to channel prediction and reconfigurable intelligent service. Additionally, we're also exploring the application of generative AI in these areas. Next is a rate splitting multiple access. This is another huge branch of wireless communication research. When serving different users who demand the independent data packets, simultaneously transmitted data symbols for different users contaminate each other's signal and work as an interference, and we call this interference inter-user interference. However, the independent data packets can be packaged into the common message and transmitted to all users. In the cooperative communication scenario, something like IoT, this RSMA can be used to enhance the service quality. Next is the body channel communication. This is not the wireless communication, but it is possible to compare the non-conventional communication scheme based on the knowledge we've learned from the wireless communication theory. The issue on the body channel communication is that it is very difficult to infer the channel state information. Thus, the non-coherent communication that does not depend on the channel estimation has been exploited to detect the transmitted symbols. Next, I'll explain some of the experimental research areas. This human recognition using Wi-Fi channel state information study aims to estimate the number of people or their locations using Wi-Fi signals. Traditional methods using camera-based systems raise privacy concerns, and utilizing radar signals requires the installation of cumbersome equipment. In contrast, Wi-Fi stands out for its practicality, as information can be gathered through already installed routers. Wi-Fi signals are transmitted and received in the form of data containing propagation information, known as CSI, which stands for channel state information. However, this data includes noise caused by hardware defects, so pre-processing is performed to extract features. These refined data are used as input for a machine learning model, specifically a meta-learning model in our study. Wi-Fi signals are subject to continuous interference due to uncontrolled environments such as external communication and changes in reflectors over time. Meta-learning is designed to adapt to these interference conditions by learning the environment, enabling the model to continue performing human detection tests effectively even in changing conditions. Next, when a model is trained on outdated data, the model is directly applied to a new testing environment, accuracy drops to 24%. However, by applying the MAML, which is a model agnostic meta-learning, one of the most widely used meta-learning models, we achieved the accuracy of over 90% with only a minimal adaptation sample of around 10. Lastly, the future wireless communication systems demand on very high speed, low latency, and reliability within limited frequency bands. Visible light communications, also known as VLC, using LEDs as transmitters and photodiodes as receivers, offers a promising solution for short-range communication. Operating in the 400 to 790 terahertz spectrum, this VLC provides enhanced security functionality and limited penetration. Future 5G and 6G networks aim to leverage VLC for high physical layer security. Additionally, VLC is very cost-effective, utilizing existing infrastructure, and it combines illumination with the communication while consuming very minimal power. So this is the end of my presentation, and if you want to know more about our lab, please visit our website. Thank you very much for your attention, and if you have any questions regarding the research areas, he is a PhD student in our lab, and he will be very happy to answer them. Thank you very much. Do you have any questions?
Can you talk about the detail how to do the low resolution ADC at the beginning? How to do that low resolution ADC?
Exactly, low resolution ADC needs to use less complex power. So actually, I don't know these details of this research because I don't. This is not my the project. Yes, I know the researcher uses the message passing algorithm for using the quantization in low resolution ADC, because if we use the low resolution ADC, there the system can form some kind of quantization error. So we have to deal with the